Okay, here's 4.8, analyzing graphs of polynomial functions. So I've got this graph in front of me here, and I'm looking at these 3 points, which are kind of like vertices, but they're not called vertices because it's not a parabola. So these are called turning points or extrema, and each one of them is either a maximum or a minimum. Okay, so these two are going to be minimums, and this one is a maximum. Let's take this point. Yeah, it's a minimum, but it's not the minimum of the whole function. Because it's not the lowest point on the entire graph. So this is just a local minimum. It's the lowest point in its neighborhood, right, in this section of the graph here. But there's a point that's even lower than that down here, or there's many points, but that's the lowest point overall. So this point is going to be called the absolute minimum. Or you could say that it's the minimum of the entire function, right? So you see the difference there. That local one's just in its area, but this is the overall lowest point in the graph, okay? And this is the only maximum that I see on the graph, but there are points that are higher up than that point, right? So this is also just going to be a local maximum. This doesn't have an absolute maximum because it goes up forever. Okay, so those are the extrema or turning points, all right? All right, so to find those, there's a number of ways you can do it, but at this point, the only tool we have at our disposal is a graphing calculator. Okay, so I've got this example here. So if I wanted to graph this, I could start making an XY table and start finding XY pairs and eventually make a graph. But it would be really useful to have these minimums and maximums plotted. Okay, one point I will plot is the y-intercept, because if you plug in 0 for x in both positions, both those terms will become 0, and then y would equal -3. So hey, I know that's going to be my y-intercept right there. Okay, so I'm going to use a TI graphing calculator here. Okay, let me get. I want to first just put this equation into my calculator and using the y equals button in the top left. Okay, I've got another equation there, so I'll just hit clear. All right, I'm doing 2x to the third, and when you type in your x, you want to use this variable button right there, right below mode. Okay, and then let's see, plus 7x squared minus 3. Okay, and once you got that in there, then hit the graph button in the top right. Okay, if you've got a different zoom going on, you could hit zoom and go to zoom. I've got zoom standard right now, which is kind of just 10 ticks in each direction. That's usually where I like to start. Sometimes you need to zoom out or in to see what you need to see. And I can see, okay, that I do have a y-intercept at -3, just like I had predicted. Okay, but and it actually looks like it's really close to that minimum. Okay, but we'll find exactly where that is. Maybe it's right on the y-intercept, maybe not. But let's find this point first, okay? So what I'm going to do to find this one up here, I'm going to go to the calc menu, which is right above the trace button. So I'm going to hit second trace to get to the calc menu, okay? And I was looking for the top of the the top of that. That would be a maximum, so I'm going to find a maximum. Okay, now there's only one maximum on the screen here. It would be up here, right? But sometimes on some equations you might have different maximums on the same screen, so we need to tell our calculator which maximum we're looking for, even though there's only one here. So the first question it's going to ask at the bottom of the screen, it says left bound question mark. So what I do, I move my cursor around using these arrow keys until the cursor is to the left of the maximum that I'm looking for, and then I'll hit enter. Okay, and then right bound, I'll put my cursor to the right of that. Okay, so now my calculator knows that I'm looking for a point in between the left bound and right bound, And the last question, it says guess, question mark at the bottom of the screen there. So then I'm just going to move the cursor close to the maximum, somewhere up there, and I'll hit enter. And so right before I hit enter, it has these decimals, but when I hit enter, it's going to narrow, when I still have decimals, but they're slightly different decimals. And it's a little hard to see here, but it will give me the coordinates of that XY pair. Okay, so finding the one of my maximum, this would be my local maximum, is going to be, it's about negative 2.3 and 9.7. Okay, so it's about those. So now I can plot that on my graph. So let's see, negative 2.7 and 9.7. That's going to be somewhere up there. I'm just eyeballing this. But yeah, that's about, and this is approximate, right? So this is negative 2.3, 9.7. Okay, all right. So let's repeat the process, though, now looking for this point, for that minimum, that local minimum. So I'm going to hit second trace again to get to calc, and then I'll go to minimum this time, and I'm going to do a left bound, right bound. So I'm putting my cursor to the left of that point down there, hitting enter. Then I'll put my cursor to the right and hit enter, and then I'll move it close to the minimum and hit enter one more time. And then that minimum is actually, it does happen to be the y-intercept. So it's the point 0, negative 3. Okay, which I already had plotted because I knew that was the y-intercept. That's interesting. I just made this equation up, and it just so happened that minimum was the y-intercept. Okay, so now I can sketch this in, and I've got those two very important points in my graph. And you could get other xy pairs. I'm just going with the basic shape for now. Now we could find the x-intercepts as well. That might be handy by plugging in 0 for y and then trying to factor it, although that one's not going to be factorable. But okay, there we go. All right, so that's the idea with finding minimums and maximums using your calculator at this point. Later on, you can use calculus to find those points as well. All right. Okay, on the next page, we're going to look at even and odd functions. All right, and it's a little confusing because you might think, so looking at these examples down at the bottom of the page, you might think, oh, hey, this is going to be an even function because it's fourth degree. It's an even degree. And this is an odd function because it's third power function, third degree function, so it's an odd degree. That works sometimes, but not all of the time. So the degree of the equation isn't actually telling you if it's an even or odd function, okay? So even and odd functions, this is not the same thing as a function with an even and odd degree. Yeah, it's unfortunately confusing like that, but that's how it is, okay? So here's what an even function is. An even function is going to have symmetry about the y-axis, okay? So just to make a little sketch here, let's say we have a parabola that is centered on the y-axis. Well, this would be an even function because if you reflect it over the y-axis, it'll look exactly the same. It'll map onto itself. That would have symmetry about the y-axis. Okay. An odd also, this is going to be true. F of x is going to equal f of negative x from like an algebraic perspective. Okay. An odd function is going to have symmetry about the origin, which is the same as rotational symmetry about the origin. Okay. All right, so here's my origin, right? So I'm going to draw a function that would have, and this is just a little sketch, but maybe if I had something like this, if you imagine rotating that about the origin, so if you stuck a pin in the origin and started turning it like that, like a clock, if you turned it 180 degrees, it would look the exact same. It's just a sketch, so I was trying to make it symmetrical like that. But it would look the same, right, if you turned it upside down. That would mean it would have rotational symmetry about the origin, which means it would be an odd function, okay? Algebraically, f of negative x is going to be equivalent to negative f of x, okay? So one way with these equations to see if it's odd or even is to graph them, and you can tell sometimes by looking at it. It's just, it's hard to tell. Maybe you have a parabola that's not quite centered on the y-axis, but it's very close, or same thing with rotational symmetry. But you could look at the graph. What I'm going to do is use these tests for even and odd functions, okay? So let's do I always like to do the even test first. So I'm asking myself, is this function even? Well, if it is even, then f of x should equal f of negative x. Well, I already know what f of x equals here, so let's find out what f of negative x equals. So that means I'm going to substitute in, where the x's are, I'm going to substitute in negative x. Okay? Now, I need to simplify this. So, and this is negative x times negative x times negative x times negative x. You can write it all out like that, but anytime you take a negative number and you're raising it to an even power, it's going to come out positive, right? You can think negative x times negative x comes out to positive x squared. Well, this is going to come out to positive x to the fourth plus x squared minus 1. Okay, so then I'm looking at this, hey, that's the same as my original function when I simplified it. So my answer here is yes, it is even. Okay, and I don't need to test if it's odd if I've already found out that it's even, because it's not going to be both. There are some very rare functions that would be both, but I'm just going to stop once I've done one, once I have a test that works. Okay, so that one's going to be even. All right, so then over here, let's do a test for even here. Asking myself, is this even? So let's see, let's find f of negative x. And take the opposite of negative x squared. Make sure to use parentheses, that's going to make a difference. Okay, this is going to come out to positive x squared there. Okay, and then I've got negative x squared plus 5. Well, my answer is going to be yes again. This is another even one. Okay, all right. So let's try this one. So even, let's see, is this even? Let's find f of negative x. Okay, and I'll simplify this. When I'm raising a negative number to an odd power, it's going to come out negative. And that will be plus 7x. Oh, okay, so my answer here is no, it's not even. So then I'm going to test if it's odd. Just because it's not even doesn't mean it's odd. It could be neither one, okay? So let's test out odd. Okay, so here's my test at the top of the screen for odd. I already know what f of negative x equals. It equals, this is f of negative x right here, right? Now I want to see if that's the same as negative f of x. So I need to find negative f of x, okay? That means I'm taking the opposite of f of x. F of x is equivalent to all of that. I'm taking the opposite of the whole thing. It's not as simple as just putting a negative in front of the x to the third, though, because I'm taking the opposite of both terms. So I want to set it up like that and then distribute the negative. So this is going to be negative x to the third plus 7x. I forgot the negative. Negative x to the third plus 7x. There it is. Okay, and those are equivalent, right? And now I can see negative f of x is equal to f of negative x. These are the same thing. Yeah, this isn't equal to the original function, but it's equal to f of negative x, and that's what I'm checking for odd. So this one's odd, okay? Let me separate these a little bit. Okay, so let's try another here. Let's test if this is even first. So I want to find f of negative x. Okay, so a negative raised to an odd is going to come out negative. So this would be negative 2x to the fifth. Okay, that's not the same as the original, so it's not even. Let's check if this is going to be odd. So let's look at negative f of x. I want to see if negative f of x comes out to negative 2x to the fifth. It doesn't have to be equal to the original. It has to be original to f of negative x. Okay? So I'm going to take the opposite of all of this, and there's only one term there. So that's negative 2x to the fifth. Hey, those matched up, and this one then is odd. Okay? And I know what you might be thinking. Well, I don't know, but I'm guessing some of you might be thinking, wait a sec, you said that it's not the same. Well, these have, as looking at the degree, well, these have degrees of 4 and 2, which are both even numbers, and they came out even. These ones are both have odd degrees, and they came out as odd functions. So it seems like it matches up, and honestly, usually it does, but there are cases when it doesn't. Okay? So let's look at this. So let's check if this is even. So looking at this, you might think, oh, that's going to be odd, but let's check it out. So f of negative x got this, okay? Raising to an odd power gives me a negative, okay? And raising to an even power, and raising a negative number to an even power comes out even. Okay, so hey, that's not equivalent to the original, so it's not even. Let's test if it's odd. So I want to see what negative f of x equals. Oh, I'm running out of space here. This equals, let's see, the opposite of the whole thing. Wait a second, those aren't quite the same, right? The 5x squared terms are different signs, so this one's going to be a neither. Okay? So that can happen sometimes. All right, let's test this one. Let's see if it's even or not. I'm checking f of negative x. Okay, it's not even, right? That's different than the original. Let's test if it's odd. I want to see if this comes out the same as f of negative x. So if it comes out to negative x plus 1. So let's see. I'm taking the opposite of the whole thing. And when I distribute, those are not equivalent. They're a little different. So it's not odd either, so this is also going to be neither. Okay? All right, that's the end of the section, and I will see you next time.